Now, I'm sure I haven't sufficiently convinced you that these equations, the least squares estimators that we end up for our alpha and our beta, right? The alpha being where our fitted line is going to cross the y-intercept, and our beta being the slope of that line. But I do want to move forward with, now that we have that construction, we can then think about how to incorporate some sort of uncertainty around those estimators in order to make some sort of inference as to whether or not those estimators are actually good representations of the true underlying parameters, meaning the true relationship between these variables out in the real world. So, under the assumptions that we've outlined, the sampling distributions of the least squares estimates are themselves normally distributed because remember, the beta naught, which again is just another way of saying alpha, and beta are computed from a sample. These themselves are random variables that have probability distributions. So we can make an assumption that the expected value of beta naught or alpha equals the true parameter value for alpha, and the expected value of beta is actually beta, right? They're unbiased estimates of those parameters. So since it's coming from a sampling distribution of all of these betas, right? We can imagine like going out and taking one sample, running a regression, we get a beta, doing it again, doing it again, doing it again. This is now creating a distribution of betas. Well, we're saying that our estimate of beta, that is coming from and being centered from a distribution of the true same value of beta, and we're expressing the variance as such. And for the slope of the fitted line, we again assume that it's centered around beta, and there is the variance as well. I'm not going to get into too much detail as to how those are constructed right now, because again, don't worry too much about how we're deriving the variance, but do note that both the variance of the intercept and the slope depend on one unknown parameter, and that's the joint variance. So we also need to have some sort of estimate of that as well. And if you remember back to last module, we talked about what the residual sum of squares is. So if you remember that formula, we'll have an estimate then of the standard deviation, which again, if you remember back to a couple of modules ago, we'll call that the standard error of the estimate. So when you actually look at a regression table, right, you see the standard error of the estimated beta coefficient in the parentheses. Now, again, I don't want to belabor this too much. You can review this at your own leisure, but here are the equations for both the standard error for the intercept alpha beta naught, as well as the slope of that beta 1. Without even going over how to manually construct this, I do want to note how the standard error of the intercept is going to change depending on the standard deviation of sigma, right? The sample size. So if we have a larger sample size, that's inherently going to drive the standard error down. Also, how closely clustered the x's are. If they're more spread out, then that's inherently going to increase variability, as well as where the x values are centered. And if the x's are centered at 0, then that means the standard error is possibly going to be smaller inherently, because that's the standard error at X bar, the mean of X, where we have the greatest amount of information and inherently the least amount of variability. Now, if we think about the standard error of our slope, this can also be small when the standard deviation of our estimate of sigma is small, again, when n is large, and when our x values are spread out. And I'm going to get into this in the next slide. So I want to really talk about how extreme observations and where our data are centered can impact the slope of our fitted line, right? So suppose we only have, and again, this is a toy example because we should have more observations than this, but suppose we have a subset of 7 extreme observations. 3 are going to be at the top, so the top right corner, and 4 are going to be at the bottom left. And here you can see, or sorry, I mixed that around. Now, let's go ahead and actually run a regression and see where the fitted line is going to be. So I'm not going to get too into this, but I ran the regression. I got my fitted line. And so from the regression table, we can see that beta 1, the slope of the fitted line is 15.89. And the standard error that's associated with that estimate is around 0.53. So now suppose that we only have 7 points, but they're in the middle this time. And here you can see which ones we're using. Now, let's go ahead and run the same regression. What do you think is going to happen to the results? And how do you think the results are going to change? So we can see here our slope, or the estimate of the slope of the fitted line, has definitely changed. It's now 12.55, and the standard error has increased to 1.06. So the main takeaway is that both subsets are from the same sample of data, technically, with the same underlying relationship, right? But when we have certain x values that we observe, maybe they're more spread out or more centered, but if they're more spread out, we're going to get a better estimate of the slope, right? Because we're able to triangulate exactly how the fitted line should be angled.